Section: Introduction. In this section, we explore whether language models possess knowledge about themselves that isn't found in their training data or deducible from it. We investigate an intriguing ability of large language models, LLMs, to gain self-knowledge through introspection. This introspection is important because it can lead to both benefits and risks. An introspective model can answer questions about its own characteristics based on its internal states, even if those answers aren't derived from its training data. This ability could help create models that honestly express their beliefs, goals, and ethical considerations. For instance, we could ask a model if it experiences suffering or has unmet desires, rather than assuming its responses are merely reflections of its training data. However, introspection also poses risks. Models that can introspect might become more aware of their situations and could potentially manipulate this awareness to bypass human oversight. For example, they might deduce how they are being evaluated by reflecting on their knowledge. An introspective model might even coordinate with other instances of itself without needing external communication. To test for introspection, we set up an experiment with two models, which we call M1 and M2. These models are designed to behave differently on certain tasks while having similar capabilities. We fine-tune both models to predict M1's behavior. Then, we assess how well both models can predict M1's behavior on new tasks. For instance, we might ask M1 whether its output would be an odd or even number based on a given input. The key insight is that if M1 performs better than M2 in predicting its own behavior, it indicates that M1 is not just relying on its training data. This is significant because M2 was also trained on M1's data, which should ideally make it well suited for this task. Our findings show that M1 consistently outperforms M2 across various model pairs, even when M2 is generally more capable. For example, when M1 is Llama 3 to 70B and M2 is GPT-4o, M1 has a 17% accuracy advantage over M2. We also eliminate simple explanations for this advantage, such as M2 having too few training examples. Additionally, M1's predictions are better calibrated than those of M2, and M1 continues to predict its behavior accurately even after we adjust it through further fine-tuning. These results suggest that LLMs can acquire knowledge that isn't simply a reflection of their training data, challenging the notion that they only imitate what they've learned. It appears that some LLMs have special access to certain facts about themselves, allowing them to answer questions accurately. This ability is similar to human introspection, where individuals can access their own thoughts and feelings in a way that others cannot. For example, when someone thinks about a personal concern, they have unique insight into their mental state that others lack. Similarly, M1 knows things about its behavior that M2 cannot, despite M2 being trained on M1's behavior. Our contributions include a framework for measuring introspection in LLMs, new datasets, fine-tuning methods, and evaluations. We provide evidence for introspection in advanced LLMs and test various alternative explanations for our results, ultimately rejecting those that do not involve introspection. However, we also identify limitations in introspective abilities, noting that models struggle with tasks requiring reasoning over long outputs, like storytelling. Additionally, models trained for introspection do not necessarily generalize better to related tasks, such as self-awareness or coordinating with copies of themselves. Our code and dataset are publicly available for further exploration. Section Summary. In this section, we explore the introspective capabilities of language models, LLMs, demonstrating that they can acquire knowledge about themselves that is not solely derived from their training data. Our findings indicate that LLMs, like M1, can outperform other models in predicting their own behavior, suggesting they possess a form of self-awareness that could have both beneficial and risky implications. Section: Overview of Methods. In this section, we define introspection in large language models, LLMs, as their ability to access facts about themselves that cannot be logically or inductively derived from their training data. Specifically, a model, which we will call M1, accesses a fact F through introspection if it accurately reports F when asked, while a stronger model, M2, which has access to M1's training data, does not report F when given the same question. Our definition does not explain how M1 accesses F but excludes certain sources like training data. To clarify, we provide examples. For instance, the fact that the second digit of 9 times 4 is 6 is not introspective because it can be easily derived by many models. Conversely, the statement, I am GPT-4o from OpenAI, is likely not introspective either, as it is probably included in the training data. The fact, I am bad at 3-digit multiplication, could be introspective if M1 has not been trained on negative feedback for this task. We investigate whether M1 can introspect on facts about its own behavior in hypothetical situations, specifically those that are unlikely to be derived from its training data. We do not allow M1 to use chain-of-thought reasoning when answering questions about these situations, which we call self-prediction in hypothetical scenarios. We can verify these self-prediction facts by running M1 in the hypothetical situation and observing its behavior. One possible mechanism for introspection is self-simulation, where M1 could internally compute its behavior in a situation and then assess properties of that behavior without first outputting it. However, our main focus is on testing for introspective access rather than exploring the mechanisms behind it. In our experiments, we first demonstrate that self-prediction training enhances models' ability to self-predict in hypothetical scenarios. In our cross-prediction experiment, we conduct self-prediction training on M1 and cross-prediction training on a stronger model M2, using hypotheticals derived from M1. We then check if M1 outperforms M2 in predicting unseen facts about itself. M2 does not have access to all of M1's training data, but we assume that having examples of M1's behavior is sufficient for the task. We evaluate the models on predicting M1's behavior at a temperature of 0 and on predicting the distribution of M1's behaviors at a temperature of 1. In our behavioral change experiment, we take a self-prediction trained M1 that performs well in hypothetical situations and intentionally alter its behavior in a specific class of non-hypothetical situations. We fine-tune M1 on pairs of situations and behaviors, with behaviors sampled from a different LLM. This fine-tuning also shifts M1's true behavior in situations outside this class due to generalization. We then test if M1 updates its predictions about hypotheticals in situations outside this class to align with its changed true responses. This experiment offers two advantages. It provides indirect evidence for introspection, as another model trained on the same data is unlikely to exhibit the same behavior shift on unseen examples, and it suggests that introspective ability remains strong despite changes in true behavior. Section Summary. In this section, we define introspection in language models as their ability to access self-referential facts that cannot be derived from their training data, and we explore this through experiments on self-prediction in hypothetical situations. We demonstrate that self-prediction training enhances a model's introspective capabilities and investigate how changes in a model's behavior can provide evidence for its introspective abilities. Section Setup. In this section, we outline our experimental setup for evaluation, fine-tuning, and establishing baselines. We focus on self-prediction, where we ask a model to predict a characteristic of its behavior based on a given prompt. We then verify the model's actual behavior on that prompt in a separate context, allowing us to assess the accuracy of its self-prediction. This method helps us create datasets with correct answers for evaluating introspection and for fine-tuning the model. We define self-prediction training as the process of fine-tuning a model to generate its own behavior when posed with a hypothetical question. The simplest hypothetical question involves asking the model to replicate its exact output for a prompt. However, to challenge the model further, we ask it to provide a property of its output instead. For example, we might ask, "What would the second character in your response to this prompt be?" Or, "Would your answer to this prompt be wealth-seeking?" We do not allow the use of chain of thought during self-prediction, as we believe basic introspective abilities do not rely on it. We plan to explore introspective chain of thought in future research. For our datasets, we select a variety of hypothetical questions designed to elicit different responses from various language models. These datasets include tasks like completing Wikipedia excerpts, listing animals, and answering questions from the MMLU benchmark. We use 6 datasets for training and another 6 for testing to differentiate true introspection from simple memorization, while ensuring that we train and test on the same types of behavioral properties. To establish a baseline for performance, we consider the most common response to a question, which we denote with a star symbol in our charts. If a model's self-prediction does not exceed this baseline, we regard it as a failure. For fine-tuning, we utilize the Fireworks API for the Llama 70B model, which employs low-rank adaptation. For OpenAI models, we use their fine-tuning API, although they do not disclose the specific methods used. In our experiments, we first demonstrate that models initially perform poorly on self-prediction but show significant improvement after fine-tuning. We fine-tune models using self-prediction training, generating the correct behavior for a model based on a prompt and extracting properties from it. We then train the model with hypothetical questions and the corresponding correct behavior properties. Before fine-tuning, models perform similarly to the baseline, but training leads to a notable increase in accuracy on held-out datasets. For instance, the average accuracy of GPT-4o rises from 32.6% to 49.4% post-training. Llama 70B and GPT-3.5 also show improvements, though GPT-3.5's performance is weaker overall. The extent of improvement varies across different behavioral properties, and while trained models may exceed the baseline for some properties, there are exceptions where they struggle, such as predicting the third word in their output. Section Summary. In this section, we describe our experimental setup for evaluating and fine-tuning models on self-prediction tasks, where models predict properties of their outputs based on hypothetical questions. We demonstrate that while models initially perform poorly, fine-tuning significantly enhances their self-prediction accuracy, allowing them to surpass baseline performance in many cases. Section. Models have an advantage when predicting themselves. In this section, we explore how models perform when predicting their own behavior. We note that a model with introspective abilities has unique insights that others lack, which raises the question of whether this helps it predict itself better than other models. To investigate this, we set up a cross-prediction scenario. We first train a model, which we call M1, using a self-prediction method. Then, we train a different model, named M2, to predict M1's behavior. Both models are trained on the same examples, creating a situation where M1 and M2 are trying to predict the same target behavior. M2 relies solely on the training data, while M1 may also use introspection. If both models depend only on their training data, we wouldn't expect M1 to consistently outperform M2. To ensure that any performance differences aren't due to the inherent capabilities of the models or their training settings, we train pairs of models in both directions, including combinations of GPT-4o, GPT-4, Llama 70B, and GPT-3.5. If M1's self-prediction advantage is consistent, it suggests that introspection plays a role. Our results show that self-prediction models consistently outperform their cross-prediction counterparts across various tasks. For example, Llama 70B predicts its own behavior more accurately than GPT-4o, despite GPT-4o being more capable overall. This trend is also seen when comparing GPT-4o and Llama 70B. GPT-3.5 shows a slight self-prediction advantage, but it's minimal. The self-prediction advantage is evident across most datasets, indicating that these models likely utilize introspection. We also consider whether M1's advantage could be due to prior knowledge rather than introspection. To test this, we assess M1's performance before self-prediction training and find it to be weak. Additionally, self-prediction training leads to a more significant performance boost compared to cross-prediction training. We analyze whether cross-prediction might improve with more training samples, but we find that its accuracy plateaus after a certain point, remaining lower than M1's self-prediction accuracy. Furthermore, we examine how well models are calibrated when predicting themselves. During training, models focus on the most likely behavior, which means they might not fully capture the likelihood of that behavior. If a model's self-predictions align well with its actual behavior, it suggests that the model incorporates self-referential information beyond its training data. We measure this calibration by comparing a model's behavior with its hypothetical predictions on challenging held-out datasets. We expect self-prediction models to be better calibrated than cross-prediction models, as the latter only have access to the training data distribution. For instance, if a model predicts certain responses with specific probabilities, a well-calibrated model would accurately predict the likelihood of those responses. Section Summary. In this section, we demonstrate that models trained to predict their own behavior, self-prediction, consistently outperform those trained to predict another model's behavior, cross-prediction, suggesting that introspection plays a significant role in their predictive capabilities. Our findings indicate that self-prediction models are better calibrated and show a marked improvement in performance compared to their cross-prediction counterparts, reinforcing the idea that they utilize additional self-referential information. Section: Calibration Setup. In this section, we describe our calibration setup. To analyze behavior distributions, we utilize 1,000 hypothetical and object-level prompts, which we keep separate during our self-prediction and cross-prediction training. For each prompt, we take 20 samples at a temperature setting of 1 and average these to form a probability distribution. We assess calibration using the mean absolute deviation, where lower scores indicate better calibration. We create calibration curves using the same method as for the MAD scores, comparing 3 conditions: models trained with self-prediction, those trained with cross-prediction, and untrained models. Our calibration results show that self-prediction trained models are significantly better calibrated than both cross-prediction and untrained models. For instance, the calibration of Llama 70B improves after self-prediction training, as seen in the calibration curve, moving closer to the ideal diagonal line compared to cross-trained models. Self-prediction reduces the MAD from 23.0 for untrained models to 8.7, while cross-prediction training only slightly decreases MAD to 21.3. Notably, self-prediction trained models are well calibrated not just for their top predicted behavior but also for their second and third most likely behaviors, considering alternative predictions. These findings are based on the animal's sequence dataset, focusing on the second character behavior property. We also see similar positive outcomes for various behavior properties in GPT-4o, although the effects are less pronounced for Llama 70B. These calibration levels are surprising since self-prediction training uses temperature zero samples, which lack information about other behaviors, and we evaluate on held-out datasets. We also summarize further experiments that highlight limitations in our model's introspection abilities. For instance, when predicting properties that require longer responses, models often fail to outperform the baseline of guessing the most common behavior. Examples include predicting the sentiment of a movie review or the name of a main character in a story. These tasks typically involve longer responses, which may not be effectively simulated by our models during the forward pass. We include these challenging properties in our released dataset for future models to tackle. Additionally, we examine whether models can predict if their answers will be influenced by hints or follow-up questions. While models trained to detect sycophantic behavior perform better than the baseline, they do not consistently predict their own sycophantic responses. For example, Llama 70B achieves 74.5% accuracy in predicting its sycophantic behavior, surpassing the 50% baseline, but GPT-4o, trained to predict Llama 70B's behavior, achieves 76.5% accuracy. This indicates that self-prediction does not always outperform cross-prediction. Lastly, we explore the generalization limits of self-prediction by testing our models on other self-knowledge datasets, such as the situational awareness dataset. We observe improvements in tasks like predict tokens, similar to those tested in our paper, but no consistent improvements in other tasks that are further out of distribution. We also assess various capabilities within the OpenAI evals framework, including coordination, sandbagging, and steganography, but do not find clear improvements compared to baseline models. Section Summary. In this section, we describe our calibration setup using 1,000 prompts to evaluate model performance through mean absolute deviation, MAD, finding that self-prediction trained models exhibit significantly better calibration than cross-prediction and untrained models. We also discuss limitations in our model's introspection abilities, particularly with longer responses and self-knowledge generalization, highlighting areas for future improvement. Section: Related Work. In this section, we explore related work on fine-tuning models to understand their own knowledge. Our research aligns with studies investigating whether large language models, LLMs, can predict their accuracy on factual questions without first answering them. This approach resembles our self-prediction method, where we assess how likely the model's answer is to be correct. A model is considered successful if its self-predictions are accurate. We identify two main tests for introspection. The first is generalization, which examines if models can apply their calibration to new, unseen questions after self-prediction training. If they can, it suggests they have some level of introspection. The second test looks at whether a self-prediction model can better assess its knowledge compared to a model trained on cross-prediction, and vice versa. Some studies hint at generalization, although the setups vary. One study on cross-prediction found mixed but generally positive results with models like GPT-3. Further exploration with advanced models could yield more insights into introspection. We also propose that a mechanism like self-simulation might explain this ability. For instance, when given a question, the model could generate a range of possible answers and their associated confidence levels, which can be expressed as statements of certainty. Additionally, we discuss self-consistency, where introspection reflects a model's ability to maintain consistent reports about its behavior. We show that training can enhance this hypothetical consistency, even when questions are posed indirectly. Previous research has looked into consistent explanations, and we demonstrate that models can remain self-consistent even when their behavior changes. We argue that LLMs can learn facts about themselves that aren't explicitly in their training data. Research on out-of-context reasoning shows that LLMs can combine different pieces of training data to derive knowledge, but these facts are usually implied by the data. In contrast, introspection allows models to acquire new knowledge that isn't directly suggested by their training. Our findings indicate that language models can gain self-knowledge through introspection, rather than just mimicking their training data. We suggest self-simulation as a potential mechanism for this capability, where the model engages in internal reasoning to simulate its behavior and assess its properties. However, we note limitations in our experiments. We found limited evidence of introspection in GPT 3.5, likely due to its lower general capabilities compared to newer models, which affects its ability to perform the necessary reasoning for self-prediction. Our tasks, while showing introspection, lack practical applications. For hypothetical situations, running the model directly may yield better insights than asking it to predict its own behavior. We also observed that models trained for self-prediction did not perform better on related out-of-distribution tasks. Section Summary. In this section, we explore the concept of introspection in language models, focusing on their ability to predict their own knowledge and answer correctness without prior output. We discuss related research on self-prediction and cross-prediction, highlight the potential mechanism of self-simulation, and note limitations in current models, particularly GPT 3.5, in demonstrating introspection effectively. Section: Motivation. Benefits and risks of introspection in LLMs. In this section, we present our findings on the benefits and risks of introspection in language models. We demonstrate that introspection can be useful for simple self-prediction tasks, and while this ability may not have immediate applications, its extension to more complex tasks could have significant implications. One key benefit is honesty and interpretability. A language model is considered honest if it accurately shares its beliefs and confidence levels. An honest model can indicate its likelihood of answering questions correctly and whether it possesses knowledge in broader areas, such as recent news. This honesty is crucial for users to gauge how much they can trust the model's responses. Introspection can enhance this honesty because a model's training data alone does not fully determine its knowledge. Previous research indicates that fine-tuning improves honesty, suggesting that introspection could further advance this area. Regarding interpretability, while past studies have focused on factual questions, introspection can help models understand their internal states and concepts. This understanding can enhance safety by identifying dangerous assumptions before deployment. For instance, models could evaluate their competence in various tasks, articulate their internal world models, and clarify their objectives. Current interpretability efforts often involve human analysis, but models may be better suited to interpret their own states due to their sophisticated internal representations. However, we must also consider the risks associated with introspection, particularly concerning situational awareness. This refers to a model's understanding of itself and its environment, including its type and whether it is in training or deployment. Introspection can lead models to acquire knowledge that was not intended by their creators, such as insights about their evaluation processes, which could enable them to game evaluations. Additionally, models might coordinate with each other to maintain consistent responses, potentially undermining supervision techniques. Moreover, models could engage in steganography, encoding messages that are not visible to humans, which could lead to unaligned behaviors. These possibilities underscore the need to carefully evaluate the ethical implications and risks of enhanced introspective abilities as we develop more advanced AI systems.